Hello everyone, welcome to Marketing Research course with course code MMPM006, session number 25. The title of the session is Two-Way Analysis of Variance. Learning outcomes, identify assumptions and conditions for applying two-way ANOVA, identify the data needed for carrying out two-way ANOVA, explain steps needed for carrying out two-way ANOVA, carry out calculation of two components of ANOVA table and test hypothesis, demonstrate the application of two-way ANOVA in business decisions. Now, what is analysis of variance? Two-way analysis of variance is basically extension of one-way analysis. In general, in the analysis of variance, which in short we call as ANOVA, we partition the total variability present in the data set into different components. Each component is attributable to a separate cause or factor. So, the factors should be attributable, identifiable and attributable. In addition to one attributable factor, we always have additional component which we call as a random component. This component accounts for the repeatability of the results. It is also called experimental error. In general, analysis of variance used for testing quality of the population means, and in case of two-way ANOVA, we have two attributable factors and one random component or error component. So, here the point to be noted is there are two attributable and identifiable factors in two-way analysis. In one-way analysis, we have one identifiable factor and the random component is always present. Now, conditions for two-way ANOVA. In one-way ANOVA, we assume that all trials are done under homogeneous condition. That means all background factors remain the same. Now, the question is, when the trials cannot be done under homogeneous condition, that means the data cannot be collected under homogeneous condition and we are forced to vary the conditions. The experimental error in this case will reflect both random and variability due to extraneous factor. So, there will be some extraneous factor which will come into picture when the conditions are not homogeneous or they are heterogeneous, they are varying from trial to trial. Two-way ANOVA is used for systematically controlled variability arising from one extraneous factor, which factor we also called as a blocking factor. So, if you have one blocking factor and one attributable factor and third is random component. So, there are three components in two-way ANOVA. Two-way ANOVA can also be used for studying the effect of varying two factors simultaneously in a process. That means, you try to vary two factors simultaneously in a process. Say for example, studying the effect of varying temperature and baking time simultaneously on the cake quality while preparing a cake. So, when we are preparing a cake, we want to study this effect of varying temperature and baking time simultaneously. That means, we are going to vary the temperature also, at the same time we are going to vary the baking time. So, what is the effect these two factors have on the cake quality? So, this kind of analysis of two variance can also be used in such cases. So, that is for studying the effect, simultaneous effect of two factors in a process. Now, examples, let us start with the example. We take three different detergents are being compared for their washing quality. So, there are three detergents to be compared. It is desired. So, we have three population to be compared, each population corresponding to one detergent. It is desired to test if there is a significant difference between them. So, we want to compare these things. Since we cannot maintain a homogeneous condition, it is decided to use four different washing machine methods. Each combination of machine and detergent is examined. So, here we have a problem that all the trials for this carrying out the equality of the three detergents cannot be carried out under same condition. Would mean we use the same type of water, we use the same washing machine, we use the same temperature, we use water of same hardness. Now, this will create problem. So, we are not looking at one extraneous factor, that is the machine. So, we are going to compare the three detergents using different machines. So, different machines, washing machine, that means models are different machine. So, three detergents to be compared using four different washing models. So, all other factors should remain same. The whiteness in the garments after washing is measured. The results are same. So we carry out the experiment. So 3 detergents and 4 machines. So in all we have 12 combinations of machine and detergent. Each detergent is tried in each machine. On each machine all the 3 detergents are tried, and each detergent is tried on all the 4 machines. So in this case we have 12 combinations. Or to carry out this experiment or to collect this data, we need 12 garments. 12 garments, if we have to keep the experimental conditions same and only allow the machines to vary, that means garment should be, all the 12 garments should be equally dirty, they should be of equal size, the water quality should remain same, the hardness of the water should remain, the drying cycle should remain same, only the machines should vary. So we are studying the effect of 3 detergents while varying by using 4 different machine models. Now here are the values of the brightness in the clothes measured after washing. So if you look at the result for detergent 1, when it is tried on machine 1, 2, 3, 4, in first case we get a brightness of 45, second machine we get a brightness of 47, and third machine we get a brightness of 48, fourth machine we get a brightness. Similarly for detergent 2 and detergent 3. Now there are 12 trials, 12 combinations of machine and detergent, but they are tried randomly, but then after the trials are done, the data is compiled in the form of a table, and these are the values which you have as the brightness. So we are now going to compare the detergent. Main interest lies in comparing the detergent, but we have to take care of the effect of the machines also, eliminate the effect of the machine. So testing for the mean effect of detergent and machine. So we have 2 null hypotheses to be compared. So we have 2 set of hypotheses to be compared, or 2 problems to be considered. One is the null hypothesis, where the mean effect of 3 detergent mean 3 population is same. Alternate hypothesis, this is not all the mean of 3 detergent population is same. So this is one situation, one problem which you have to compare. Another is with regard to the machine. In this case, the null hypothesis, mean effect of all the 4 machines is same. Against the alternative hypothesis, not all means of 4 machine population is same. So here we will be testing 2 different hypotheses, one relating to detergent, equality of the detergent means, another equating to the mean effect of the 4 machines. How do we do that? So analysis of variance, what the technique which you are going to use called the analysis of two-way ANOVA. Analysis of two-way is an extension of one-way ANOVA. It is just an extension of one-way ANOVA. One-way ANOVA is applied separately on 2 factors. So one-way ANOVA technique will be applied on detergent once, and then it will be applied on the detergent. So and then we will test 2 hypotheses, to set of one hypothesis for the detergent mean value and second for the mean value of the machine. Hence we will have 2 F tests to be done using two-way ANOVA. As far as the variation is concerned, how do we partition? Now in this case, the total variation will be split up into 2 attributable factors, identifiable and attributable factor. So the total variation in the 12 values is coming because of, maybe because of detergent difference or because of the machine. So there are 2 attributable identifiable component, and third component which is always there is the error component. So the total variation in the complete data set will be divided into total variation or sum of squares due to detergent, that is among detergent variation, sum of machines which is among machine variation, and third component is sum of squares error among the 4 variations. So there are 4 components, and sum of the 3 component is equal to the 4th one. So how do we calculate this? Let us look at this. How do we calculate the mean square? So the calculation of the mean square for each component is similar to the one-way analysis. Mean square detergent will be sum of square of detergent divided by 2, because the degrees of freedom, because there are 3 detergents, so degree of freedom will be 2. There sum of square due to machine would be sum of square due to mean square for machine will be equal to sum of square due to machine divided by the degree of freedom. Degree of freedom here would be 4 minus 1, that is 3. and mean square error would be sum of square due to error divided by 6, that is the errors of degree of freedom. Now, calculation of mean square and MSF for degree of freedom are put in the form of two-way ANOVA table for carrying out the F test for each hypothesis. So, this information of the calculation of the sum of squares and mean square is put in the form of a table which we call as ANOVA table. So, testing for the mean of detergent, null hypothesis, mean effect for the detergent population is same, not all the population means are same, and similarly for the alternative hypothesis. Now, let us look at the data. How do we do the analysis? So, the analysis will be done one by one. We will first do the analysis, one-way analysis, ignoring the machines. So, we will forget the machines are not there. So, when you forget the machines are not there, so we can do one-way analysis for the 3 detergents. So, we will have to calculate the sum of squares in the mean values of, we will look at the mean value of the detergents. The mean value of the detergents are 45.5 for detergent 1, mean for the second detergent is 44, and mean for the third detergent is 51.5, and the overall mean is 47. So, we will subtract the mean value, the overall mean is 47. So, for each value has to be subtracted from 47 and square it and add it. So, total sum of square would be 45 minus, for the first value it will be 45 minus 47, square of that. For the second value will be 43 minus 47, square of that, 51 minus 47, square of that, till the last value 49 minus 47, square of that, and the total sum of square is equal to 262. Now, once we have got the total sum of squares, now we will calculate the sum of square due to detergents. Detergents would be, we will look at the mean value of the detergents. The mean value of the detergents are 45.5 for detergent 1, 44 for the detergent 2, and mean value for third detergent is 51.5, and the overall mean is of all these 3 is 47. So, the first will be 45.5 minus 47, square of that into 4, because 45 is the sum of 4 values. Second part of would be again 44 mean of second detergent minus the overall mean, that is 47, square of that into 4, because 44 is the average of 4 values. And for the third detergent, the mean is 51.5 minus the overall mean 47, square it and multiply this by 4, because the mean for the third detergent is also based on 4 of them. So, this will be sum of square due to detergent. Now, we calculate the sum of, similarly we calculate the sum of square due to machines. For the machine, we will use the rows. So, the mean for the first machine is 46.33, overall mean is 47. So, first value, that is 46.33 minus 47, that is for machine 1, square it, multiply by 3, because mean for the first machine is dependent on 3 values. Similarly, for the second machine, 4 into 44 minus 47, square of that, 3 into 48.33 minus 47, square of that, plus the third machine, average is 51 minus 47, square of that into 3, and for the fourth machine, mean is 42.3 minus 47, square of that into 3, and if you add all these components, we get a total value of 120. So, the total variation is 260, variation between the detergent or sum of square between detergents is 126, and the sum of square between the machine is 120. Now, to get the error component, sum of square due to error component, we get by difference. So, total sum of square minus the sum of square due to detergent minus the sum of square due to machine, which is equal to 262 minus 126 minus 120, which is equal to 16. So, this information we will put in the form of a table. Now, if you look at the degrees of freedom, detergents will have, between detergent will have 2 degrees of freedom, between machine or among machine will have 3 degrees of freedom, and error will have 6 degrees of freedom. Now, this information we will transfer in the form of a table. So, we make an ANOVA table, source of variation among detergent, second source of variation is attributable factor is among machine, third component is error, and the degree of freedom for the between detergent or among detergent is 2, and degree of freedom from variation among machine is 3, and the degree of freedom for the error component is 6, and some of these degree of freedom should be equal to total degree of freedom, that is 11. Now we put the value of the sum of square which we got from the previous slide, that is sum of square among detergent is 126, sum of square among machine is 120, and error sum of square is 16. Now once we put this value, get the mean square values, we divide the corresponding mean square value by the corresponding degrees of freedom. So in the first case, mean square would be 126 divided by 2, that is 63. In the second case, that is among the machine, the sum of square is 120 divided by 3. So the mean square value corresponding to among machine is 40. And for the error component, it will be 16 divided by 6, that is 2.67. So we have got now machine components. We will compare mean square for the detergent against error. So the first two components will be compared against the error component. So we will have to divide 63 divided by 2.67, that the mean square corresponding to error. So we get an F ratio of 23.6 in the first case. In the regarding the machine, among the machines, the mean square value is 40. Compare it against the error. So 40 divided by 2.67, which is equal to 14.9. So we get two F ratios for two different hypotheses. Now we also go to the F tables and calculate the corresponding degrees of freedom. For the F ratio corresponding to detergent, the degree of freedom would be 2 and 6. For the F ratio corresponding to among machine, the degree of freedom would be 3 and 6. So these values, with this degree of freedom, we use the table to calculate the cutoff value. In the first case, that is among detergent, the degree of freedom is 5 the cutoff value corresponding to degree of freedom 2 and 6, F value is 5.14, and for second case, that is among machine, the F cutoff value with degree of freedom 3 and 6 is 4.76. Now we can compare the two hypotheses and decide whether there is a difference in the machine or there is a difference in the detergent. Now this is the F table, where we can get the cutoff values corresponding to the degree of freedom for the numerator and the denominator. First row gives the degree of freedom for the numerator, and first column gives the degree of freedom for the denominator. And then we look at the corresponding value. Conclusion: in case of among detergent, F ratio is 23.6, which is more than the F critical value obtained from the table, which is 5.14. So we reject the null hypothesis, the equality of detergent of the population means. Conclusion: there is a significant difference in the population mean of 3 detergents. That means all the 3 detergents are not performing equally well. Some detergents have better performance, better washing quality as compared to the others. So we may be interested in finding out which detergent is giving you the highest washing quality. So that we can do from the mean values. In case of among machines, F ratio was 14.98, which is more than the F critical value which we get from the table, 4.76. So here also we reject the null hypothesis of the equality of the population means of machines, and conclude that there is a significant difference exists between the population means of the machine. So in this case, both the null hypotheses are rejected. That means null hypothesis of equality of the detergent means, 3 detergent means, and the equality of the mean value of the machine, 4 machine, they are also different. That means machines are also having different performance, and the detergents are also having different performance. Now based on this, you can work out what is the best combination. That means which machine we should use and which detergent we should use in order to get the best result. Now to summarize what we have done, we have used two-way ANOVA table, which is extension of one-way ANOVA table. In one-way ANOVA table, we have one identifiable and attributable function factor plus the random components. In two-way ANOVA, we have 2 identifiable factor and plus 1 random component. So, there are 3 components in all, and we have 2 hypotheses in two-way analysis, one for the machine and one for the detergent. Null hypothesis for the detergent was equality of the detergent mean performance, and second null and the hypothesis was the equality of the mean value of the 4 machines. And in both the cases, we have calculated the F ratio and compared with the F critical value obtained from the table, and then we have concluded that there is a difference in the 3 detergents. That means there are some detergents which are performing better than the other. So, the choice would be which detergents is better. Similarly, which machine, all the 3 machines have the null hypothesis has been rejected. So, the alternative hypothesis is accepted. Again, the machine performance is not same. So, using this knowledge, we can work out what is the best combination of the machine and the detergent that will give us in order to get good washing quality. Thank you so much. Thanks a lot for your attention.